Hey everyone! Today, we're going to tackle one of the biggest, most important ideas in all of calculus, the limit of a function. And trust me, this is a big one. It's basically the foundation that everything else, derivatives, integrals, you name it, is built on.
So to get our heads around this, let's start with a kind of weird question. Imagine you've got this function, and it's working perfectly fine everywhere, except for one single tiny point where it just breaks. It's got a hole in it. So how in the world do you talk about what's happening right at that spot?
Okay, here's a classic case. We've got this function, and we want to know what's up when x equals 2. But when we try to just plug in the number 2, we get 0 divided by 0. And in math, that is a huge red flag. It's called an indeterminate form, which is a fancy way of saying we have no idea. It's a mathematical question mark. Our easy method just failed, so we're going to need a better tool.
And that is where our investigative toolkit comes in handy. We're going to attack this problem using something called the rule of 3. The best way to think about it is like we're detectives looking at a mystery from 3 totally different angles to make sure we don't miss anything.
So, here's the plan. First, we're going to look at the raw numbers, just making a table to see what happens as we get ridiculously close to that problem spot. Then, we'll draw a picture, a graph, to really see what's going on. And finally, we'll break out the algebra to get a definitive, rock-solid proof. 3 angles, 1 single answer.
All right, let's grab our first tool and look through the numerical lens. Now, we know we can't just plug in 2, but what if we just sneak up on it? What happens if we plug in numbers that are super close to 2?
Whoa, okay, look at this pattern. See what's happening? If we come from the left side, 1.9, 1.99, 1.999, the function's output gets closer and closer to 4. And look, the exact same thing happens from the right side. We plug in 2.1, 2.01, 2.001, and the answer is zeroing in on that very same number, 4.
So, the evidence here seems pretty overwhelming, doesn't it? All the numbers are basically screaming at us that the answer has to be 4. It really feels like we've already cracked it. Case closed, right?
Well, not so fast. And this, right here, is one of the biggest lessons you learn in early calculus. The numerical approach feels convincing, but sometimes it can be a total trap. It can straight up lie to you.
Let me show you what I mean. This function, sine of pi over x, is the perfect example of this danger. If you just check a few numbers close to 0, like 0.1 or 0.01, the answer is always 0. You'd be totally convinced the limit is 0. But in reality, the function is going absolutely bonkers, oscillating like crazy between -1 and 1 an infinite number of times. The limit doesn't even exist. And that's why numbers are great for a hint, but they are never, ever proof.
Okay, so let's switch to our second tool, which is usually a lot more intuitive for us humans. Let's try the graphical approach. Let's just look at the thing. What does this function actually look like?
See, a picture really is worth 1,000 words. Looking at this graph, you can clearly see with your own eyes that as you trace the line towards x equals 2 from either side, you're heading straight for a height, a y value of 4. But right at that spot, there's a hole. The function's actual value at x equals 2 is that other dot way up at 6. And this shows the main idea perfectly. The limit is the journey, it's where you're heading. The function's value is the destination, where you actually land, and they don't have to be the same place at all.
Okay, the graph gives us some fantastic intuition. But to be 100% mathematically certain, we need our third and most powerful tool, algebra.
And this is the crucial point. Looking at a table of numbers or a graph, that gives you a really good guess, an estimate. But algebra gives you the cold, hard proof. It's the tool that erases all doubt.
Now, for a lot of nice and well-behaved functions, like polynomials, there's a really simple rule called the direct substitution property. All it says is that if you can just plug the number in without breaking math, like dividing by 0, then the limit is just whatever value you get. It's the best-case scenario.
Let's see this in action. For a simple polynomial like this one, finding the limit as x goes to 3 is as easy as it gets. There are no holes, no tricks, no weirdness. You literally just plug in 3 for x, do the simple arithmetic, and boom, the answer is 14. That's it. So let's go back to our original problem, the one that gave us 0 over 0. This is where algebra gets really cool. We can do a little simplification. That top part factors into x minus 2 times x plus 2. And now we can cancel out the x minus 2 on the top and bottom. This little trick basically mathematically plugs the hole for us. It shows our tricky function behaves just like the simple line y equals x plus 2 everywhere except for that one single point. And now we can use our direct substitution rule on this new simple function. Plug in 2, you get 2 plus 2, which proves beyond any doubt that the limit is exactly 4.
So we did it. We found our limit. But does this process always work? Think back to that crazy sin pi over x example. Sometimes, even with our full toolkit, we discover that there just isn't a single number that the function is approaching. And in those cases, we say the limit does not exist.
And there are usually three main culprits for this. The first is oscillation, where the function just bounces back and forth forever like a pinball, never settling down. The second is unbounded behavior, where the function just shoots off to infinity or dives to negative infinity. And the third is a jump, where the graph approaches one value from the left side and a totally different value from the right. If any of these things happen, there's no single limit.
So, after all of that investigation with our different tools, what is the single most important idea that you need to walk away with? It's this. This is the absolute core of the entire concept. The limit is only about the journey, the behavior of the function as it gets closer and closer to a point. It couldn't care less about the destination, what's actually happening at the point itself, or even if there is a point there at all. It's all about the approach.
And that really leads to the final amazing thought. This whole idea of a limit lets us analyze what's happening at these invisible, infinitely small spots where things seem to break down. It's our first real step into a world where we can understand things like instantaneous speed and infinite series. So it leaves us with a bigger question. If we can use this tool to see into these mathematical holes, what other hidden behaviors in physics, in economics, in the world all around us, can calculus help us finally understand?